Okay, so you're here because you want to understand the big complex ideas, but you don't want to wade through all the jargon, right? You want the insights, and you want them clearly and maybe with a little fun along the way.
That's us, right.
Exactly.
Yeah.
That's what these deep dives are all about.
And today we're taking on, well, I'd say a pretty ambitious project. We're going to try and explore dilation theory and dynamic behaviorism
Whoa.
as a potential way to unify our understanding of...
Everything.
Yeah, really everything.
So we've got some really fascinating material to work with here. It looks at this pretty novel framework and some of its mind-blowing implications.
For sure.
So what's our mission here today? We really want to pull out the core of these ideas for you.
Yeah.
We're going to focus on the fundamental concepts, look at some potential real-world applications.
Whew, like what?
We'll think cutting-edge tech and even a new angle on UAPs.
All right.
And we're going to try and wrap our heads around a very radical new view of time itself.
It sounds like...
Yeah.
Yeah, it does. And this isn't just, an intellectual exercise. This framework actually aims to bridge the biggest gap in modern physics, the one between quantum mechanics and general relativity.
It's a big one.
So where do we even begin to unpack something this huge?
Well, I think a good place to start is with the bedrock, dilation theory.
Oh, right.
Which suggests that time isn't actually a fundamental dimension, not in the way we typically think of it, like length or width.
Okay.
Instead, it proposes that time is something that arises from the existence and interactions of all things.
Even things that maybe aren't physical in the traditional sense.
Right.
So time isn't just this, universal clock ticking away at the same rate for everyone.
Not according to this theory.
Okay.
Dilation theory introduces the idea of a fifth dimension that's connected to what's called entropic time. And
this isn't like, regular time, like on a clock.
This isn't your grandfather's clock, no.
Okay.
Think of it less like a straight line and more like a fluid.
Something that can be stretched, squeezed, sped up, or slowed down depending on different conditions.
That's a pretty wild departure from our everyday experience of time.
It is.
So where does this dynamic behaviorism come into play?
Well, dynamic behaviorism offers a really interesting complementary perspective. It says that how anything behaves, whether it's a tiny particle or a massive galaxy, is determined by its specific properties at that exact moment, that now...
Interesting. So the properties in this moment dictate what happens next.
Exactly. It's like saying the characteristics of a single frame in a movie dictate what happens in the next frame.
So the universe at any given instant is defined by the properties of everything in it.
Yeah.
And those properties are what dictate what happens next at every scale.
You got it.
That sounds like it could be a way to actually connect the very small and the very large.
That's precisely the potential.
Okay.
Dynamic behaviorism offers a possible route to what our sources call a geometric unity of the scales. It hints that the same fundamental rules governing behavior might apply across all levels of reality, from the quantum to the cosmic.
Okay, so let me see if I've got this straight. Dilation theory gives us this fluid, emergent time in a fifth dimension.
Right.
And dynamic behaviorism tells us that the present moment and its properties drive behavior everywhere.
Yeah.
So how do these two kind of core ideas link up to give us this new understanding and maybe even bridge that quantum cosmic divide?
Well, the potential unification lies in the idea that the properties dynamic behaviorism talks about are deeply intertwined with this emergent fluid time described by dilation theory.
Correct.
The underlying symmetries in how these properties manifest across different scales.
Okay.
They're linked to the conservation of this entropic time. It's this interplay, this dance between emergent time and the properties of the now that the framework suggests could resolve those apparent contradictions we see between the quantum world and the universe described by general relativity.
Wow, so it's like time itself is the canvas on which the properties of reality play out.
That's a great way to put it.
Our sources really drill down on this idea of time being more than a moment.
Yeah.
What does dilation theory actually say about how we usually think about time passing?
Well, traditionally, our understanding of time has been very anchored in history and often quite personal.
Okay.
Think about, ancient calendars tied to seasons or religious events.
That's right.
Dilation theory offers a shift. It says that a now moment isn't just a static point on a timeline.
Okay.
It's a dynamic behavioral event. It's packed with these unique properties, and these properties are what dictate what happens next.
So every single now is almost like its own unique little snapshot of the universe with its own set of rules playing out in that instant.
In a sense, yes, and this leads to the really interesting concept of time as a fluid symmetry.
Okay.
The analogy they use is really helpful. Imagine a stream.
Okay.
The way the water flows, its speed, its direction, any eddies or ripples, it's all shaped by the stream bed and the banks. Those act as boundaries.
Right. Faster currents where the channel is narrow, slower pools where it widens out.
Exactly. Now, dilation theory suggests that mass and energy act as similar boundaries to the flow of time, but in this fifth dimension we talked about,
Okay.
they essentially slow down the flow of time just like a rocky stream bed slows down the water.
So regions with more mass or energy have a different temporal current than empty space.
Precisely. And they even give us a mathematical way to represent this time dilation effect, a function that takes into account relative velocity, they call that VAB, and the gravitational field, GB, it looks like this, FVAB, GAB.
That equation looks familiar.
Yeah.
Like it has echoes of relativity in it.
It does indeed.
Okay.
And they offer a simplified version as well, relating time dilation to something called flow differential with this function, F-flow differential. Flow differential, they think of flow differential as a measure of the difference in that temporal current we were just talking about.
Okay, so the bigger the difference in this temporal flow between 2 points, the more time will be dilated between them.
That's the core idea.
Okay.
And perhaps even more profoundly, the theory links inertia.
Okay, an object's resistance to changes in its motion.
Right, to this very time dilation effect, stating inertia and flow differential.
Wait a minute, so you're saying inertia isn't just this inherent property of mass that we've always thought it was. It's actually connected to how an object interacts with this flow of time.
That's what they're proposing.
That's a really fundamental shift in perspective.
It truly is. Now let's maybe focus a bit more on the concept of time dilation itself. We know from Einstein's special relativity that time passes at different rates for observers who are moving relative to each other.
Yeah, the faster you travel, the slower time passes for you compared to someone who's standing still.
Right, one of those mind-bending consequences of relativity.
Exactly.
And this is quantified by what's called the Lorentz factor, with this standard formula, nunner 4 and nunner 4 nuni 40 cc2. Dilation theory offers its own interpretation of this factor. It sees it as a ratio, the ratio of how time flows in a particular gravitational field or within this fluid of time compared to how it flows in a vacuum far away from any gravitational influences.
So the Lorentz factor isn't just about how fast you're moving through space, but also about the temporal environment you find yourself in.
Precisely.
Wow.
And they introduce a modified Lorentz factor that includes the gravitational potential, VC3.
Okay.
This is a key addition because it explicitly shows how gravity affects the flow of time, which is a central tenet of dilation theory.
Right.
It's like both speed and the depth of a gravitational well both contribute to how time gets stretched.
So both motion and gravity warp time, according to this updated equation, gravity creates its own kind of drag on this temporal fluid.
That's a very intuitive way to think about it.
Okay.
Now let's dive maybe a little deeper into this notion of temporal mechanics in the fifth dimension. Dilation theory really paints a picture of time as this dynamic temporal hydrodynamic environment existing within a fifth dimension.
A fifth dimension that's essentially made of time itself.
Yes.
That's a concept that really makes you stop and think.
It does. And this environment arises from applying the fundamental laws of conservation, like the conservation of energy and momentum, to this emergent entropic time we discussed earlier. It's not just a static backdrop. It's a dynamic realm where time itself can exhibit hydrodynamics, it can have ripples and even eddies.
So the very structure and behavior of the cosmos, from the swirling of galaxies to the formation of stars, is somehow influenced by these ripples and eddies in time.
That's what the theory suggests.
That's a completely new way of looking at cosmology.
It is, and they even propose a connection between the complexities of quantum information, that fundamental stuff that underlies quantum mechanics, and dilation. The idea is that dilation stress, the variations and gradients in this flow of time, is what we actually perceive as gravity.
So gravity isn't a fundamental force in the traditional sense, like electromagnetism, but more of a consequence of the stress in this temporal fluid caused by the underlying quantum information of the universe.
Yeah.
That's a truly mind-bending thought.
It certainly pushes the boundaries of our current understanding. And to handle this fluid-like nature of time mathematically, dilation theory employs tensor calculus. It suggests a revision of the metric tensor, that mathematical object that describes the geometry of spacetime in Einstein's theory, but extending it into 5 dimensions.
So Einstein's field equations, which so brilliantly describe gravity in our familiar 4 dimensions, would need an upgrade to account for this extra temporal dimension.
Exactly. The theory proposes extending Einstein's field equations to 5 dimensions to incorporate this temporal hydrodynamic environment. The equation itself looks similar in form, but with the indices now running from 0 to 4, indicating those 5 dimensions. 12 RGAB plus C ETG.
So we can see the similarities and differences there.
For sure.
And how does this bridge the gap back to the incredibly small world of quantum mechanics?
Well, dilation theory attempts to make that connection by considering quantum field theory, or QFT, our best current framework for describing the quantum world. It suggests replacing the traditional stress-energy tensor in those 5-dimensional equations with the expectation value of the energy-momentum tensor operator, the datetime. This is a way of bringing in the inherently probabilistic and quantum nature of matter and energy into the description of space-time itself.
So these revised 5-dimensional equations incorporating quantum principles could potentially give us that long sought-after unified description of the universe at all scales.
That's the ambitious and very exciting goal. And mathematically, this involves extending the standard 4-dimensional metric tensor, which we use to measure distances and time intervals in space-time, into a 5-dimensional version represented as G, where I and J now range from 0 to 4. This expanded mathematical framework is designed to capture the more complex geometry of this expanded temporal spacetime.
So we've been talking about some really fundamental and abstract concepts.
We have.
But let's shift gears a little bit and talk about some of the potential real-world applications, starting with this intriguing idea of grok stuff, metamaterial design, and its possible connection to UAPs.
Ah, yes.
This sounds like something straight out of science fiction.
It does have that futuristic feel. The theory proposes a conceptual metamaterial design rooted in the principles of dilation theory, with the very ambitious goals of achieving superconductivity, the ability to conduct electricity with 0 resistance, and a 0 inertia state. This would theoretically be accomplished by carefully manipulating the behavior of electrons within the material, and crucially by manipulating time dilation at a very local level.
0 inertia, that's the stuff of dreams for advanced propulsion, isn't it? Imagine being able to accelerate instantaneously without feeling any of those crushing g-forces.
Precisely. The proposed metamaterial has a layered structure, with each layer engineered for specific properties. There's a superconductive layer using high-temperature superconductors, a time dilation layer made of materials with a high or even negative refractive index to potentially manipulate the speed of light, an electron manipulation layer designed to extend the wave functions of electrons, and an inertia-canceling layer using materials with exotic properties like high negative compressibility.
So it's like this incredibly complex sandwich of materials.
It is.
What are some of the major hurdles in actually creating something like this in a lab?
Well, they're very upfront about the highly speculative nature and the immense technological challenges involved. Operating at temperatures near absolute 0 for sustained superconductivity is one major hurdle. Precisely controlling time dilation at such a small scale without creating paradoxes is another enormous challenge. Preventing the formation of Cooper pairs in the superconductor while simultaneously manipulating electron behavior is also critical, as those pairs are what enable superconductivity in the first place. And then, as you mentioned, simply finding or even creating materials with those highly unusual properties like significant negative compressibility needed for the inertia canceling layer is a massive unknown.
So this is very much in the realm of theoretical engineering at this point.
Absolutely.
But if hypothetically we could build a craft using such a metamaterial, what kind of incredible attributes might it possess, according to this framework?
Well, the potential capabilities are quite extraordinary. We're talking about perfect superconductivity, a complete lack of inertia, the experience of time passing at a faster rate relative to the outside world for those inside unusual and extended electron behavior in the outer layers of the material active inertia cancellation, and of course the very nature of being constructed from this multi-layered metamaterial incorporating high-temperature superconductors and those specialized electron manipulation and time dilation layers.
A faster relative rate of time inside the craft. That's a mind-bending concept.
It is.
What kind of implications might that have?
Well, it could potentially be linked to the zero inertia state as a consequence of manipulating the flow of time locally, according to the theory.
Okay.
Now, this is where the really intriguing but also highly speculative connection to unidentified aerial phenomena, or UAPs, comes into play.
Okay, this is where it gets really interesting. How do these potential attributes of a theoretical metamaterial craft line up with some of the characteristics reportedly observed in UAPs?
The zero inertia state could potentially explain the often reported ability of UAPs to exhibit anti-gravity lift instantaneous acceleration and hypersonic velocities without any apparent means of propulsion or any discernible g-forces on board. The faster time rate inside the craft and the active inertia cancellation could also contribute to those incredible acceleration capabilities. Low observability or even apparent invisibility might be linked to the metamaterial design and the potential for manipulating electromagnetic radiation, including light, through engineered refractive indices, and even time dilation effects. And the ability to move seamlessly between air and water transmedium travel could also be a consequence of having zero inertia and potentially manipulating the craft's interaction with different mediums through localized time dilation.
It's a fascinating, albeit highly theoretical, a potential explanation for some of these persistent mysteries. The idea that manipulating time at a fundamental level could unlock these seemingly impossible capabilities is truly mind-blowing.
It certainly stretches the limits of our current technological understanding.
Yeah.
Now, for anyone listening who might be thinking, this is such a revolutionary idea, someone should patent it, our sources actually do provide a general overview of the patenting process.
Good to know for any future time-bending inventors out there. What are the basic steps involved in trying to protect an invention like this?
Well, the process typically begins with meticulously documenting your invention, including very detailed descriptions and any prototypes or experimental data you might have.
Okay.
Then a crucial step is to conduct thorough research into existing patents to ensure that your idea is genuinely novel and hasn't been patented before. Next comes the preparation of the patent application itself, which includes a comprehensive written description of the invention's specific claims that legally define the scope of what you're trying to protect, and detailed drawings if applicable.
Okay.
This is often a stage where seeking guidance from a registered patent attorney is highly recommended.
Makes sense.
Once the application is filed with the relevant patent office and the necessary fees are paid, the application enters a phase of prosecution, where patent examiners review your application and may raise objections or request clarifications.
Gotcha.
If all goes well and you successfully address any concerns, the patent is eventually granted, and you then need to pay periodic maintenance fees to keep the patent in force for its full term.
So it's a rather involved and often lengthy legal and technical process. Any other key pieces of advice for potential inventors based on our sources?
Well, they emphasize the critical importance of maintaining strict confidentiality about your invention before you file a patent application. They also advise carefully considering the potential commercial viability of your invention and being prepared for the significant time and financial investment that the patenting process can entail. For our listeners in the United Kingdom, they even provide the contact information for the UK Intellectual Property Office.
Very helpful.
Yes.
What about the actual structure of a patent request? What kind of information do you typically need to include in your application?
A standard patent request will generally include a clear and concise title for your invention, a background section that explains the relevant technological field and the specific problem that your invention aims to solve, a summary of the key features and advantages of your invention, a brief description of any accompanying drawings, a very detailed and enabling description of how your invention works and how to make or use it, the crucial claims that legally define the boundaries of your intellectual property protection, an abstract that provides a concise overview of the invention, the drawings themselves if needed to illustrate the invention, and finally, various administrative details such as inventor declarations and payment of the required filing fees.
So it's not just about having a groundbreaking idea. You need to be able to articulate it with extreme precision and navigate a rather complex legal and bureaucratic landscape.
Precisely. Now let's maybe circle back to some of the more philosophical and fundamental implications of dilation theory, particularly the intriguing concept of the now moment.
Yeah, this idea of the now being more than just a fleeting instant. It kept coming up in our sources.
Yeah.
How does dilation theory actually define or describe this now?
They characterize the now as an eternal dynamic moment.
Okay.
It's not simply a dimensionless point on a timeline that instantly vanishes. Rather, it's an active and ongoing event where the specific properties that exist at that moment in time dictate the behavioral outcome of everything within the universe.
So the entire universe at every scale is constantly being shaped and influenced by the specific configuration of properties present in this ever-present now.
That's the implication. They suggest that all fundamental elements of existence share similar underlying properties and a common directionality within this fifth temporal dimension we've been discussing. And it's this shared directionality that gives rise to our perception of a consistent arrow of time.
And what role does the act of observation itself play in this picture of the now?
Observation, according to the theory, isn't just a passive recording of what's already there. It becomes an added property of the now moment. This highlights the inherent contextuality of reality, suggesting that the observer isn't a detached bystander, but actively participates in shaping the observed outcome. It's like the act of looking changes what you're seeing.
So reality isn't a fixed objective thing that exists independently of us, but something that's constantly being co-created and influenced by the now and the very act of observation.
That's the direction in which dilation theory seems to point us. The now in this framework isn't just a passive present. It offers a fundamental key to understanding both the nature of existence itself and the seemingly relentless flow of time.
It's a profoundly different way of thinking about our place and our role in the cosmos.
For sure.
And this concept of contextuality seems to be a recurring and important theme within dilation theory.
It is indeed a central tenet. The theory posits that the behavior of fundamental particles isn't solely determined by their intrinsic isolated characteristics, but also crucially depends on the observational context in which they are being examined. This aligns remarkably well with the established principles of quantum contextuality, which we see in quantum mechanics.
So the act of measurement in the quantum world isn't just revealing a pre-existing property, but is actually, in some sense, influencing or even defining that property at that moment.
Precisely. And this leads to the broader and rather radical idea that reality itself might be more accurately described as a dynamic and fundamentally contextual construct, rather than a fixed and objective entity that exists independently of any observers. The theory even suggests that the inherent dualities we observe in the universe, like wave-particle duality and quantum mechanics, might be manifestations of underlying geometric symmetries within this expanded framework, hinting at a potentially virtual or abstract nature of reality, somewhat reminiscent of the holographic principle.
And our sources specifically mention the work of Jens Eisert in quantum information theory in relation to this idea of contextuality.
Right.
How does his research connect with dilation theory's perspective?
Well, Jens Eisert's work on quantum information theory, particularly his research into the nature of entanglement, that bizarre phenomenon where particles become linked regardless of the distance separating them, strongly resonates with the contextual nature of dilation theory. Entanglement demonstrates how the measurement performed on one entangled particle can instantaneously influence the state of its distant partner. This interconnectedness and dependence on measurement context strongly supports the idea of a deeply interwoven and contextual reality that dilation theory proposes, where the properties of the now are not isolated, but fundamentally relational.
It all seems to converge on this idea of a universe that is far more interconnected, fluid, and observer-dependent than our everyday classical intuition might lead us to believe.
Absolutely. Dilation theory and dynamic behaviorism taken together offer a truly radical departure from many traditional views of physics, suggesting that time itself, the very fabric of our experience, is not a fundamental constant, but rather an emergent and dynamic phenomena deeply intertwined with the properties of the universe at every instant.
So as we can bring this deep dive to a close, what are the key takeaways that you think will really stick with our listeners after this exploration?
Well, I believe the most crucial points are the fundamental shift in perspective viewing time, not as a rigid dimension, but as an emergent fluid property arising from the interactions of everything in a fifth dimension. This is deeply linked to the idea of each now moment being a dynamic entity with specific properties that govern the behavior of reality, as described by dynamic behaviorism. This unified framework offers a completely novel way to think about gravity with the exciting potential to reconcile it with quantum mechanics, and even opens up theoretical possibilities for understanding incredibly advanced technologies like zero-inertia propulsion and the enigmatic characteristics of UAPs. And perhaps most profoundly, it suggests that our perception of time and the very act of observation are not passive, but are intrinsically connected to the fundamental fabric of reality itself.
It's definitely given me a lot to ponder, and I have no doubt it's done the same for you. This deep dive into dilation theory and dynamic behaviorism has definitely opened up some fascinating new avenues of thought, and as always, the questions it raises are just as intriguing as the answers it tentatively provides.
Agreed. There is a vast and potentially revolutionary landscape to explore within this framework, and we've really only begun to scratch the surface today.
So here's that final provocative thought for you to take away and consider. Could our very perception of time be the key to unlocking a more fundamental and complete understanding of the universe and our place within it? Perhaps the seemingly solid and linear reality we experience is far more fluid, interconnected, and context-dependent than we currently imagine. Thanks for joining us for this deep dive.
Thanks for listening.